All right, so let's do another example. So let's have our differential equation be dy over dx is equal to 2y. And my instructions for you are to draw a slope field. And so you should have out graph paper. And just at the lattice points, you can do it in the interval -2 to 2, both for x and y. I got it from -3 to 3 for both x and y here. And it's a lot of points. Do as many as you need to see the pattern. And then also I want you to draw in a couple solution curves in the different regions on which the curve behaves differently. If that is unclear, hopefully you'll see it in the slope field when you draw it, and if not, don't worry, we'll get to that explanation in a little bit. So pause the video and go try to sketch this out. All right, so dy over dx is equal to 2y, so what is this telling us? This is telling us that the slope of the tangent line to some function y is twice the y coordinate. So let's just start at the origin and go from there. So the origin, the y coordinate is 0, and 2 times 0 is 0. So at the origin, we're going to have a slope of 0. So we'll have a line segment like this, okay, at the origin. Now, this has a similar property to the last example. The last example only had x in the expression, and the y value didn't matter in the calculation of the slope. Now here, this expression only has y, and x doesn't matter in the calculation of the slope. And so now if I choose any other point that has a y coordinate of 0, then I'm still going to get a slope of 0. So 2, 0, and 3, 0, -2, 0, -1, 0. So all along the x-axis, the tangent lines are going to be horizontal. So my slope field line segments are going to be small little horizontal line segments. And this is going to help me when I go to create my graph. I don't have to make a large table here. So if I go down, and it doesn't really matter whatever the x value is, as long as the y value is 1, then 2 times 1 is going to give me 2 as the slope. So all of the line segments at y equals 2, these are all parallel going sideways here. Try to hit the points as best you can, like this. I'm doing all these quickly and obviously free-handed, so it's hard to do accurately. Now, if I went up to a y coordinate of 2, then I'm going to double that. I'm going to get 4, and so these things are going to start to get steep quickly here, like this. And these, again, are all parallel in this direction, horizontally. Now, if I went at y equals 3, then of course I'm going to get a slope of 6, but I don't want to worry about drawing that. So let's go down. If we did -1, then we get a slope of -2. So it's going to be something like this. And then if we did at -2, then we're going to be -4. We're getting the opposite effect of what we got above, or just maybe a reflection. Whoops, I skipped that one. Reflection about the x-axis. So it's starting to look like this. And so hopefully your slope field looks like this also. All right, so I wanted to do a better hand drawing version of this. So I paused the video, and this is what I created. Right? Anyway, this is what a slope field computer generated would look like, with a lot more little segments, more densely packed throughout the plane. And hopefully you could see some patterns here. My question to you would be, what do you see as the solution curve? What is the shape of the solution curve here? What kind of function is it, just by looking at this? I hope you would recognize it from the actual differential equation, because we talked about it in another video recently. And so perhaps you remember what I said, but if not, that's okay. You could still see in here the shape of what's going on. Like I said, I wanted you to sketch some solution curves, so I'm going to do that here, or have the computer do it for me. And so you can see, like, if I choose all these different points here, you can see the shape of it. Hopefully you're recognizing all of these curves as exponential curves. Okay. So as I mentioned, to sketch a solution curve in the different sections, meaning where the shape changes, shape's different. Above the x-axis, the exponential curve is concave up increasing, and below it's concave down decreasing. So we want to represent at least a few solutions in each of those regions. But there's one other region that's a trivial region, or not a region, I should say, one other solution that seems kind of trivial, but it's still a solution. I'll see if I can hit it with the pen here and get it to do exactly here, but sometimes I missed a little bit. I'll try one more, I'll try a couple more times. Nope. I can't quite get it, so I'm going to have to use something more precise. I'm going to tell it to draw a point here. I'm going to use 0 as the y-coordinate. If I use 0 as the y-coordinate, and actually let me use a different color here too so you can see it stand out from all the red. I'll use a green. And let's draw that one right there. So you can see if you actually start on the y-coordinate of 0, since the slope at that point is 0, the solution curve never moves off of the x-axis. It never moves off, y equals 0. And so y equals 0 is an equilibrium solution, and it's a solution. It's a constant solution that makes the differential equation true. And so that's what that looks like. So this should not be a surprise necessarily, because we saw it already. We saw that, if y is equal to a to the power of x, and then dy over dx is going to be equal to a to the power of x times the natural log of a. And so this is just the natural log of a times y, or some number times y. So 2 in this case is the natural log of some base that gives us this exponential curve. So again, we should recognize that as being exponential. We'll do one more example together, and then the rest is just practice on your own of sketching slope fields and their solution curves. And I'll put an activity together, probably on Desmos, that will allow you to get some more practice with this. And essentially, that's what this is going to be about. So let's try this differential equation. dy over dx is equal to x plus y. Now, the difference here between the previous two examples is now the slope depends on both the x-coordinate and the y-coordinate, and not just one of the two. So that's going to, not require much more work, but it's just going to require a little bit more attention, I guess. And it's not going to change as simply as the other ones. So I'm going to make a table again so I can do some calculations. I'll start at the origin, as I like to do. X plus y is 0, and so the slope at the origin is 0. That we all know that that's not always going to be the case, but happens to be the case here. Let's do another point. Let's just move up. Let's go to 0, 1. Well, dy over dx is x plus y, so I'm going to add x and y together. I'm going to get 1, and so the slope at 0, 1 is just 1. And I'll try to draw that in there like that. Let's move down to 0, negative 1. Well, that's just going to be negative 1. And so the slope is going to be opposite here. This, something like that. And now you just got to move around the plane a little bit and do a few points. Okay. Now there are some patterns that do emerge over here. For instance, if I move around a little bit, let's go over here. Let's go to 1, negative 2. And what happens if I go to 1, negative 2? 1 and negative 2 together make negative 1. That's the same thing. So at 1, negative 2, I have the same slope here. What about 2, negative 3? That's also negative 1. So I have a little bit of a pattern emerging. And if I go over to, if I stay along that line, if I go over to negative 1, 0, I still get negative 1. And everything along this line here has that same slope of negative 1. And that actually kind of is a dividing line between two different types of curves, or two different shapes of curves as it bends around. So I'll do a few more, and then I'll project the computer-generated image, and then we'll go from there. If I keep the x-coordinate constant and keep going up, then I'm just increasing by going up by 1, then I'm increasing by 1. So this is going to go up and get steeper here, or go down, it's going to decrease by 1. So this is going to be -2, and this will be -3. And same thing, if I keep the x-coordinate constant and go up, that means my y-coordinate's increasing by 1. So that means that the that the sum of the x and y-coordinate is going to be increasing by 1. So that was 0, that was 0. That's going to be 0. Yeah, that's going to be 0. That's going to be 0 as well. And we're going to have zeros along this diagonal. And so maybe you see a pattern here along a certain diagonal. Or diagonals, we can get constant slopes. If I'm at 1, 0, I also have a slope of 1, and then also along this line here, like this. This one populates pretty good. And we'll end up with a slope of 2 here along this line. Slope of 2 down here. This is going to be -2, like this. And then -3 along that line, and so forth. It's going to keep getting steeper. Okay, I'm kind of tired of drawing this, so I'm going to go get the computer-generated version going. So here's what the computer-generated version looks like, and we can see, along diagonals, all the slopes are going to be the same. Again, this is more densely populated, but you can still see this pattern in yours. I'm going to put a few things in. I'm going to dance around this line right here. You can see if we're above this line, let me see if I can get a point on this line here. -3, 2 should work. Excuse me for being a little bit slow. Should have set this up beforehand, I'm sure. And let's draw that one. And so right along that line there, that's our dividing line that keeps the things above it are concave up, increasing. I'm sorry, not always increasing. They're always concave up, decreasing then increasing here, but below they're always concave down, decreasing. I guess I got all green ones now after that. So you can see the different shapes of the curves there. So again, we could see qualities of the solution curve in different regions of the slope field, and that's why we look at these things. I'll include some examples in the Desmos activity that'll have you try to do some matching between slope fields and the differential equations, and some other things, thinking about the solution curve, stuff that we've seen on past AP exams and whatnot. Go study.